Hi, my name's Amaya.
My name's Timothy.
My name is Grant,
My name is Brennan.
and this is our presentation on our water tower design in Rukozo, Rwanda. And over the next 10 to 15 minutes, we will walk you through the humanitarian need, our Christian worldview approach, the technical design and design-making process that guided our project. The global water crisis is one of the most urgent humanitarian issues today. Lack of access to clean water leads to widespread illness and prevents communities from thriving. This is especially true in rural areas where infrastructure is limited. 2.2 billion people lack access to safely managed drinking water. Waterborne diseases like cholera, dysentery, and typhoid are leading causes of death. Rural communities suffer the most due to limited infrastructure and resources. Clean water is essential for health, education, and economic development. We chose to make our water tower in Rukozo, Rwanda, which is a rural town and a sector in the northern province of Rwanda. Located within the Gakenke district, known for its hilly terrain, farming communities, scenic landscapes, and faces multiple barriers to access safe water. Its hilly terrain and limited access to clean water makes it a perfect place for a water tower. The geographical, logistical, and economic constraints demand a sustainable and practical solution that can operate independently off an advanced grid. Rukozo has over 17,000 residents who rely on contaminated water sources. The region's hilly terrain complicates water distribution, and electricity and road access are limited, increasing logistical challenges. Our work is rooted in our faith. The Bible teaches that we are to serve others, especially those without basic needs like water, food, and clothing. This project embodies our Christian values and serves as an expression of love and care. John chapter 3, verse 11 states, John answered, "Anyone who has 2 shirts should share with the one who has none, and anyone who has food should do the same." In this verse, John calls us to share with those in need and give what we have to people who don't have. Our mission aligns with biblical teachings on stewardship and compassion, and access to clean water upholds human dignity and reflects Christ-like love. Service projects such as this one not only reflect faith, but also action. Partnerships are key to making this project viable long-term. Organizations like Living Water International, whose mission is to provide clean drinking water for struggling communities with a Christian outlook, and Water for People, who would be able to provide the tools and knowledge to complement our engineering work. Local churches such as North Phoenix and Grace Community Church offer labor, philanthropic funding, and ongoing community engagement. Ideally, we would like to partner with either of these churches, and because Rwanda is a majority Christian country, we would like to partner with a church in Rwanda to make this project a reality.
We explored 2 different truss configurations to simulate design A being this X-brace, proving structurally superior in managing lateral loads such as wind, which was critical for when we were thinking about building a tall infrastructure for the water tower. Design B was this reverse triangle. It proved less structurally sound when introducing features with the wind and the water weight, as the triangle did not tend to take off any of the vertical load.
Once we picked our designs and our measurements, we had to decide on how much water we wanted to store, which we went with 1,400 gallons for a city of 700 people, meaning we did that each person would need half a gallon of water per day. So this would be enough for a 4-day supply, which would be plenty since it rains a lot in Rwanda. And then for the force distribution of the mass, we got the 1,400 times by 8.34, which is the pounds per gallon, and this was the total force from the water capacity. Dividing that by 4, we got the force of the weight acting on each joint, and then we did that again for half capacity for the other simulation we were going to run. And then to get the wind speed, we use the equation, the force is equal to a half coefficient of drag multiplied by the air density multiplied by the cross-sectional area multiplied by the velocity of the wind squared. And we got the cross-sectional area of our design, multiplied that by the drag coefficient and the density of air. And then for the speed of the air, we got it as 9.74 meters per second. getting 4.91 for the average wind force and 19.65 when we double the wind force. And then to do the hand calculations for the first design, we would get the global FBD, and then we would get the support reactions from the global FBD by summing forces and summing moments. Once we have those, we have the support reactions at the pin and roller, which we can use to study the different joints, and studying them and doing the cross-sectional cuts, we were able to get the other forces, and the work is all present here. These were the hand calculations for design B, which were in a similar manner. First, we would get the global FBD, getting the support reactions by summing the forces and moments, and then studying the different joints, we're able to get the different forces simply by summing the moments.
We simulated each design in SolidWorks. We did 12 simulations, 6 for each design. Each simulation was with or without wind at full under or half capacity, average wind, or twice the average wind. Each simulation was a different combination of those. As stated before, we got our full capacity weight through the hand calculations, with our full capacity being under 3,000, our half capacity just over 1,500, and then our average wind speed being under 5 pounds, and twice the average wind speed being just under 20 pounds of force. We took our results and put them into this table. There's a lot of numbers, but basically to sum it up, design A was much better. The X-beams being placed at the corners helped with just distributing the vertical weight, whereas design B, pretty much all the weight was just on the beams 0, 1, and 3 to 2. The triangle beams really provided no support for the vertical load at all, and then there was really nothing to help with horizontal loads as well, whereas design A helped distribute the weight of the wind that was being pushed on the truss, as well as the vertical force was being distributed slightly more, so it reduced the vertical load, which would therefore make it a more sound and stable structure.
Once we had the hand calculation results and the simulation results, we were able to get the percent errors for each beam on the force there. For design A, we can see that the percent error has the highest one being 2.48. In design B, most of the percent errors are less, but we did have an inconsistency where the simulation got 0 force member, which was different to the one we got from the hand calculations. This meant that design A was more coherent and was more consistent, which made us think that it's more realistic and consistent, and therefore a safer option for our project.
We had 2 factors that really affected our final decision. One was price, and one was efficiency and how well it was supportive as a structure. Design B would have been cheaper to produce. However, we decided that design A was much more structurally sound and would be a lot more durable and lasting. It withstood the wind much better in the simulations, and we wanted to prioritize resilience over small things such as price. The pricing wouldn't have been much different, and so we figured it would be simpler and better and more durable to go with design A.
This is our detailed drawing for design A. This includes both a 1,400-gallon plastic tank and the dimensions of our steel truss structure. The structure was carefully planned with practical assembly steps. Every component from the supports to the coating was selected to enhance longevity and ease of construction. Our bill of materials for design A is estimated to be a total of around $9,689. While slightly over our budget, our cost reflects an investment in safety and durability. We believe this one-time cost will minimize future repair or replacement expenses. Our chart includes the tank, supports, steel frame, tools to build the tower, and the materials to make the structure last. Our instructions provide clear guidance for construction teams. With appropriate tools and labor, this can be built with basic engineering oversight in rural conditions. Our assembly includes using a cold saw to cut different dimensions of steel tubing to make the structure and attaching the supports to the base. We are using bolts and a torque wrench to secure all of our corners and the tank together. Our water tower serves up to 700 people with half a gallon of clean water daily. Clean water brings transformation. It changes lives by improving health, increasing school attendance, and enabling families to thrive. This is not just an infrastructure, it's an act of justice.
And this is just the beginning. We have vision for future expansion. We believe that with support, we would be able to expand in different sectors, such as Rwanda, which is sort of the major area where Rukozo is. We'd be able to scale our design and implement in different places. We would also collaborate with different GCU missions and the engineering teams here, helping us to expand. We could train the local residents so they could do their own maintenances, empowering them to have more leadership and faith-based development.
Thank you for watching our presentation. We're excited to continue learning and applying our engineering skills to real-world needs.
Thank
Thank you.